Lecture we have discussed Hanvenach theorem and uniform boundedness theorem. The third big theorem we will discuss today, the open mapping theorem. Open mapping theorem. This theorem basically concerned with the open mappings. Open mappings are those mappings which sends the open sets to open sets. That is, the image of the open sets under these open mappings are open. The open mapping theorem gives a certain conditions under which a bounded linear operators becomes an open mapping. So, we will basically discuss first what is open mappings, and then the open mapping theorem, what is the statement, and in proving the open mapping theorem we require the category theorem, Weyer's category theorem as a tool for proof. Okay. So, let us see what is our open mapping. Let x and y definition open mapping. Let x and y be metric spaces then an operator T from the domain dt to y with domain dt contained in x is called open mapping, is called an open mapping. If for every open set in domain dt, the image is for every open set in dt, the image is an open set in by then such a mapping we call it as a open mapping. Okay. Now, when we say that image of an open set under this mapping is open set in by, then we can have two types of possibility. One is when this image is, when the mapping is mapping the sets from domain into by, and second one when it maps the sets in domain onto its range set. So, these two types of possibilities are there. So, we should be careful while writing this statement, because both are not equivalent conditions. One is weaker, another one is stronger. So, basically we say as a note or remark, say that when we say the mapping is open, mapping is open as a mapping from its domain into by, this is the first possibility, and second is onto its range set. range set y. Now, we claim that first statement B is weaker statement, weaker than A statement. V is weaker than A. The reason is, for example, if we take a mapping, say from identity mapping I from domain dt, which is subset of x, okay, to say by, which is an identity mapping x to x, and in that case, if I consider the mapping as our first case, when x is into mapping, say here, then the x has to be open in by. Then in the first case, we can say when x is mapping, say here, the mapping x to x from x is open, the mapping in case of the first, in case of A, mapping from x into y is open if and only if x is open in y, x is an open subset of y, subset of y. While in the second case, when we say the mapping x to x is open, then automatically it is true into range set. It is an open in the range set, that is x itself, then it is automatically true, because x is already taken to be in open sets. So, this part is weaker, this is weaker and this one is stronger. Here you have to put a condition also. Okay? That's all. Now, another point which we have already noted, that earlier, that a function f is continuous function, a function f from x to y is continuous if and only if the inverse image of its open set f inverse of A is open in X for each open set A in Y. That is the inverse image of the open set. If it remains open, then such a function is said to be a continuous function and vice versa. Now, it does not mean, this does not give you that f is an open mapping. That is, it is not necessary that every continuous function is, that is, every continuous function need not be an open mapping. For example, if we take a continuous function, say mapping from R to R, and the function is say f such that f of t is sin t, where the t belongs to R. This is a continuous function, well defined function. Now, when we say f is a continuous function, when we take the image of this 0 to 2 pi under this mapping, then this mapping transferred 0 to 2 pi into a set minus 1 to 1 under the mapping sin t, because sin pi by 2 is 1 and sin minus pi by sin pi 0 to pi, sin this is a sine curve, sin 0 is 0, sin pi sin 2 pi. So, this is pi by 2, here is 3 pi by 2, okay? Pi plus pi by 2, where it is a plus sign 1 and here it is minus 1. It means this is an open set, but under the continuous function it does not transfer to a open set. So, every continuous function need not be an open set. Therefore, some extra condition is required for for a function to be an open mapping. Okay? That is one. So, this gives you the next theorem, which is known as the open mapping theorem. So, let us see the theorem now. This theorem, which is known as the open mapping theorem. Now, as a consequence, or when we add some extra condition, then we get another theorems, which is known as the bounded inverse theorem. So, basically both the theorem can be stated in a one way, stated, and we have only we require some extra condition to give the statement for the bounded inverse theorem. So, what is our open mapping theorem? The open mapping theorem says a bounded linear operator T from a Banach space X onto a Banach space Y is an open mapping. So, this is the statement of the open mapping theorem, that a bounded linear operator T from a Banach space X onto a Banach space Y is an open mapping. Okay. Now, if we bounded linear operator T from a Banach space into a Banach space Y is a open mapping, onto a Banach space Y is an open mapping. Now, if we have one extra condition, if T is bijective, then T inverse is continuous. T inverse continuous and thus bounded. So, if we put a extra condition T is to be 1 1, bijective means 1 1 on 2, then one can easily show the T inverse exists, then it will remain continuous and bounded, and this statement will give you the bounded inverse theorem. Okay. So, bounded inverse theorem say that if a bounded linear operator T is giving from Banach space to Banach space onto and it is a bijective mapping, then inverse operator will also be bounded. That is what bounded inverse theorem says. The proof of this theorem basically based on the following lemma. So, before going to the proof, we will state a lemma. The proof will based on the following lemma. Okay. What is the lemma is? So, we first prove the lemma. Okay. The lemma is, which is actually given for the open unit ball. The lemma says a bounded linear operator boundary linear operator T from a Banach space X onto a Banach space Y has the property that the image of an open ball B naught of the open ball B naught centered at 0 and radius 1, which is contained in X, under the mapping T contains an open ball about the point 0 in Y. So, what this theorem says is that if suppose this is our X and here this is say Y, both are given to be Banach spaces. These are Banach spaces. Remember this open mapping theorem and the corresponding lemma, it is valid only when X and Y both are taken to be Banach, not just like a bounded uniform boundedness theorem. We have chosen the domain X to be the Banach, but Y to be a norm space. In case of the Banach theorem, we do not require at all any completeness, simply X and Y to be a vector spaces and real or complex, and we can extend it. But here in the case of the open mapping theorem and as well as the closed graph theorem, we will see that both X and Y must be a Banach space. So, what this lemma says is suppose T is a bounded linear operator from one Banach space to another Banach space, and if I take a set B naught open ball B naught centered at 0 and radius 1, then image of this ball under B operator T must contain an ball around the point 0 in Y. So, this is the ball centered at 0 and radius Y, a ball about 0. Okay. Now, if this lemma, let us assume the lemma is true, we will prove the lemma afterward. Let us assume the lemma is true. The proof goes of the theorem goes like this. So, first proof of this theorem, proof of the open mapping theorem, and boundedness uniform boundedness theorem, and this bounded inverse theorem, we will assume the lemma is true. Okay. And let us see the first proof of this, then we will go for the proof of lemma. So, what is required to prove in case of open mapping? We want a bounded linear operator T from Banach space X onto a Banach space Y is open mapping. It means, if I picked up a open set in X, then the image of this open set X under T must be on open. That is what we wanted to show. So, let us see for every open set. So, let every open set Y has an image, let A, which is subset of X, be an open set in X. Now, what is required to prove is that image of this A under T is open in Y. This we wanted to show. So, how to prove this thing to be open? If this is our T A and we want this to be open, it means there must be some wall open set centered at T A with a suitable radius which is totally contained in Y. If I prove this part, then Y becomes open. So, basically what is required to prove is that T is open means that is to show that for every y which is the image of T x, an element of T A, for every y belongs to A, the set T A, the set T A has contains an open set in y, open set about the point y in which is T x in A. That is what we wanted to prove, okay? That this T A is open. It means if we want to take any point y whose image say T, let it be this T x which is y, and this set is our T A set, then if I find an open set centered at this point which is totally contained in T A, then T A will be open. So, that is what we want. Okay. So, let us take let y which is T x belongs to T A. Okay. Now, since A is given to be open, since A is open, okay, so it contains an open wall it contains an open wall with centered x, okay. Hence, A minus x contains an open wall with centered 0. What is the meaning of this? This is suppose x and here this is y. Now, this is the point A is, this is our set A in x, it is an open set. So, if we picked up any point x here, then we can find an open ball around this point which is contained in it. Okay. Now, if I make a transformation from A to A minus x, it means the center x will transfer to 0. So, this ball will transfer to a ball whose center is 0. That is what it said. If A is open, it contains an open ball with center A. Then now linear transformation A minus x will transfer this center x to the origin. So, corresponding ball will have the center 0. So, this will have a open ball with center 0. That is what it said. Okay. Now, let this radius of the ball be r. Let the radius of the ball V r. Okay. Now, consider or set k to be say 1 by r. So, r becomes 1 by k. Then what will be the k a minus x? The k a minus x, this will be, if suppose this is our set A, then alpha of A will be something like this. It is magnified with alpha, it is positive or negative. So, depending on, so each point x will give the position, will take the position alpha x like this. So, k of A minus x which contains a ball G at the center 0 with a radius r. When you take k of this, then the radius will be k r, and k r means it is k is 1 by r. So, it becomes 1. So, centered at 0 and radius 1, the this space will contain. Okay. So, A minus x contains open ball there, then K of A minus x contains the open unit ball V centered at 0 and radius 1. Okay, that is what. Now, let us see this lemma. The lemma says that if a T is a bounded linear operator from x to y, then image of an open ball under the operator T, whose ball is central 0 and radius 1, will contain an open ball about the point 0. So, this is an open ball here in this set, and T is an operator from here to here. So, the image of this will contain an open ball as per the lemma. So, by lemma, what we get it now is implies by lemma, it is implied that, or it is implied that the T image of this T of k A minus x, that is because T is a linear bounded linear. So, k can be taken outside, and this is T A minus T x. This thing contains an open ball, about T x is equal to y, about T x equal to y, is it not? But y is an contains an open ball about 0, not T x equal to, because this no, because this contains. So, about this will contain an open ball about 0, and so k is simply a scalar. So, T A minus T x, this set will contain a ball about 0. Therefore, T A will contain, therefore, T A will contain a ball about the point T x, y is equal to T x. Therefore, and but y is an arbitrary point, So, T A will be open, and that proves the result. Okay. So, we have shown that image of a open set under this is an open by. Clear? So, if T is a bounded linear operator, then every open set will have a open image in by. That is the proof of the open mapping theorem. Now, let us prove the bounded inverse theorem. The proof of the bounded inverse theorem, proof of bounded inverse theorem. Here one extra condition is given, that T is bijective, that is 1 1 and on 2. So, once T is bijective, so inverse will exist, and if inverse exists, and if T inverse from y to x exists, okay, then it is. Now, there is one result which we proved earlier. If T be a bounded linear operator, okay, and T is 1 1 and on 2 inverse exists, then inverse is also linear. So, this implies T inverse is linear. This was already done earlier. Okay. And again, because T inverse is linear and T is continuous, so T inverse will also be continuous. And once it is continuous, then it is bounded. So, this already we have shown earlier as in when we dealt with the norm spaces, then we have proved that in case of the linear operators, every linear operator is continuous and boundedness are the same thing. So, we have proved this. But T is linear, T inverse is exists when T x equal to 0 implies x is 0, that is one-oneness, and when T inverse is there, continuity is there, T is continuous, T inverse will be continuous and it is bounded. So, this completes the proof. Okay. So, we have proved the open mapping theorem, but what is left now? The proof of this lemma. Now, proof of this lemma we can drop or should be added. I think let us drop it, okay, or let us see the outline of the proof. Okay. Let us see outline of the proof of lemma. Let us see. So, what we wanted to prove in the lemma is that a bounded linear operator from one Banach space to a bounded linear operator T from a Banach space X onto a Banach space Y has the property that image of an open set contains an open bar beyond 0. This we wanted to prove. So, this we will prove in 3 steps. First step is we will prove the closure of the image of the open ball B1 centered at 0 and radius half contains an open ball B star. So, this the first step 1, then step 2 or step B, we will say the closure of this TBN, that is the image of the ball Bn with central 0 and radius 1 by 2n contains an open ball Vn about the origin belongs to Y, where Vn's are the ball centered at 0 with a radius 2 to the power minus n and lying in X. And third finally steps is that image of this ball B naught under T contains an open ball about 0 belongs to Y. Okay. So, these will be the steps in proving the lemma. Let us see the details of this step, proof of these steps. So, first the step 1 A. Okay. To prove this step A, let us consider the open ball. Consider the open ball B1 centered at 0 with a radius say half, which is contained in X. Okay. Now, if we picked up any point X here, okay, take any point X here, then with a suitable K, suitable scalar K, one can find out the K belongs to X belongs to K B1 for a suitable K. So, any fixed X belonging to X is in K B1 with where K is real constant, in K B1 with a K is a real constant and sufficiently large say K must be greater than 2 times norm of X. Why it is so? Because this is our ball centered at 0 with a radius half, okay, and x is this. This is our x. Suppose I take x here, any fixed x. Now, this is the norm of x, this will be the norm of x, say suppose distance from the origin. Now, if we take k times v 1, then each of these will be hinged and we get a ball around this point. Okay. This is our k b. So, k must be as large so that the x point lies within this k b. It means the radius of this ball must include this point norm of x. So, what is norm of x? K by 2. Norm of x is less than k by 2. So, if take the norm of x less than a by 2, then multiply by the radius half, norm of x becomes less than 1. It means it will include in this point b 1. Okay, that is what we want. Clear? So, that is hence. Now, x is an arbitrary point. So, we can pick up any arbitrary point here and corresponding we can find the suitable k, so that we can get in b 1. So, x can be expressed as the countable union of all k b 1 with k 1 to infinity, is it not? Every point x belongs to one of the k b 1 for suitable k, and k must be at least this one. Now, since t is given to be surjective, t is surjective. Why? Because the lemma is this. Lemma was this was the lemma. T is a mapping from Banach onto Banach. So, because of the ontoness, t is surjective. So, t is surjective. So, the image of T x, which is the whole y, is T of image of this union, but T is linear operator. So, k can be taken outside and we are getting this is union of k is equal to 1 to infinity, okay, this is infinity, k of T b 1, clear, because T is a linear operator. So, it can get the summation first k equal to 1 to m tends to infinity, T is a this we can write it T of limit union k equal to 1 to m over m and k b 1. Okay. Now, because T is continuous, limit can be taken outside and we get T of image 1 to m k b 1, and again T is linear. So, this can be taken outside and we get the 1 to infinity and like this. So, 1 to infinity k t 1. Now, can we say this is also equal to 1 to infinity k t b 1 closure? Why it is equal? Because what is the closure? Closure means it will include the limit point of these sets also, but when we take the union of all such elements in these sets when k is 1 to infinity, it is nothing but the entire y. So, it means that also includes the limit points. So, even if you take the closure of this, it is not going to change the equality sign. So, it will remain the same. So, y can be expressed as countable union of the closed set. Hence, by Weir's category theorem. Now, apply the Weir's category theorem. Category theorem, at least one of them will contain the open set by definition. So, we conclude that this set, that k t b 1 closure must contain some open ball, because what is the category theorem says is, if x is complete, then it is a of second category. It means if X can be expressed as a countable union of the closed set AKs, then one of the AK must contain the open ball. So, let us suppose that this must contain an open ball, okay? Contains an open. Say I am saying this is say B star, which is centered at 0 and radius epsilon, contained in T B 1 closure. Since K times T B 1 must contain open ball, so this will also contain the open ball, or let it be K. Okay. Then this implies the ball B star, which is V by mu naught epsilon, is contained in T B 1 closure, T B 1 closure, this bracket I am just, okay. Because K is simply an constant, we transfer the image, send the points, each point of T B 1 to K times of that point, that is all. So, if this contains the open ball, some open ball, this will also contain the same open ball which centered by naught and radius. Okay. Now, this follows, it follows that if I take a linear again transformation, that is transferring this set from by naught to origin. So, B star minus by naught will contain a ball centered at 0 with a radius epsilon in T B 1 closure minus by naught. This is also just by extension. Okay. So, this shows the first step. What is the first step? What the first step was? This was our first step. The closure of the image of an open ball B 1 contains an open ball. So, I have in the closure of the image B 1 contains an open ball B star minus by naught, okay, that contains in B naught. Now, second step, proof of second step B. Okay. So, what we proved that? We proved that B star minus by naught is contained in T B. This we wanted to prove. Okay. Where what is B naught? Where B naught is given, where V naught, this is given in this theorem, that is, this is our V naught, open ball B naught centered at 0 and radius 1 contained in X. This is our V naught. Okay. So, this we is showing. Now, what we show, this we show, this we prove by showing that T B closure, T B 1 closure minus by naught is contained in T B naught closure. Okay. T B naught closure. Okay. Now, let it be this, let it put the number, numbering is because it will require. So, let it put it this number 5 and then others number are 4, again we have to go through. Okay. What we require is B naught minus, yeah, this will be 4 like this. So, let us take only 4 3 and others number we will get. Okay. Now, let by belongs to T B 1 closure minus by naught. So, this implies that by plus by naught belongs to T B 1 closure, okay. And we remember that by naught is this, but by naught is the center of this point. So, by naught belongs to T B 1 closure already, because it is a center of that point T B1, okay, by 1. B1 was the center and we have shown that by 1 is the center, this one. Okay. So, by 1 is already in the T B1. So, it's we get this element belongs to closure of this, by naught belongs to closure of this. So, there is one result, if a point belongs to the closure, there must be a sequence of the point in T B1 which will converge to this, as well as there is another sequence of the point which converges to this. So, there exist. So, there exist the sequences W n, there exists U n which is a T W n in T B 1 such that U n will go to y plus y naught and sequence B n which is T of Z n belongs to T B 1 such that V n belongs to y naught by definition of this. Okay. V n belongs to y naught, that is okay. Where W n Z n, where W n Z n belongs to B 1. Okay. Now, since B 1 is a ball centered at B 1 with a radius say half, has a radius, since B 1 is a ball of radius half. So, we can say, so what is the norm of W n minus Z n? This is less than equal to norm of W n plus norm of Z n, and this is equal to half plus half, less than equal to half plus half, and that is 1. It means W n minus Z n, this will be the point in B naught, because B naught is a center 0 and radius 1. So, this length is less than 1. So, it will be the point in 1. And again T of W n minus Z n, that will be equal to T W n minus T of Z n, and that will be equal to U n minus B n, which tends to y. Okay. So, we are getting the point y. Therefore, y belongs to, this tends to y, y belongs to closure of T B naught. Okay. We see that. Now, since y is an element of T B 1 closure minus y naught, this shows. Okay. So, this proves our step 2. Okay. This is what we wanted to show. So, if y belongs to here, y belongs to this. So, this proves that, this proves these steps. Okay. Fifth. Now, we thus have, we have V star minus y naught, which is equal to V centered 0 with a radius epsilon is subset of T B naught, clear, and let V n is suppose 6, let V n is centered 0 with a radius minus 2 to the power minus n contained in X. Now, since T is linear, T is linear, therefore, image of T B n under this will be 2 to the power minus n T of B naught closure, and from this we get, from this we obtain. So, we get that V n which is 0 epsilon by 2 n, this will be contained in T B n closure. Okay. And this completes the proof. And step 3rd, see again. So, what we finally required to prove is that this ball V1 centered at B with a radius epsilon L by 2 is contained in TV1. This we wanted to show. Okay. So, let us take the point, let us take y as a point in V1. Okay. Then y will be, so y will be in T B1 closure. Why? Because V1 is a subset of TB1. Earlier that is proved. Okay, T1. Hence, this belongs to. So, if y belongs to the closure, it means there must be some point available in TB1 which is close to y. So, there is a V belongs to TB1 such that norm of y minus b is less than, say, epsilon L by 4. Okay? Very close to that. So, now V belongs to implies this, but V is a, so V belongs to TB1 implies that V is of the form what? Tx1 for some x1 belong B1, for x1 belongs to B1. Again Tx1 and y will be very close. So, we get norm of y minus Tx1 is less than epsilon L by 4, substituting this thing, and from here take n is equal to 2 again. Similarly, if we continue this, similarly for n is 2, we get y minus Tx1. Again this is an element belongs to V2 centered at 0 with radius 1 by 2 square, and then it contain in TB1 closure. So, difference between this again. So, there exists and x2 belongs to B such that norm of y minus Tx1 minus Tx2 is less than epsilon L by 8. Therefore, y minus Tx1 minus Tx2 belongs to V3 which is contained in TB1 closure, and so on. So, continue these steps. What we get in the last, we can choose an xn belongs to Vn such that norm of y minus sigma k is equal to 1 to n T of xk norm of this is less than epsilon L 2 to the power n plus 1, n is 1 to n, so on. Okay. Now, let us take z to be the x1 plus x2 plus xn. Since xk belongs to bk, because these are the centers, we have the norm of xk is remain less than 1 by 2 to the power k. Now, this implies, so for n greater than m, we get norm of Zn minus Zm, this is less than equal to sigma k equal to m plus 1 to n norm of xk, and this will be strictly less than sigma 1 by 2 to the power k, k is m plus 1 to n, which tends to 0 as m tends to infinity, Hence, Zn is a Cauchy sequence, but and which converges to x, belongs to capital X, H capital X is complete. capital X is complete. Also x naught belongs to V naught, since V naught has radius 1, and sigma of the norm xj x1, norm of k equal to 1 to infinity, norm of xk, which is less than sigma k equal to 2 to infinity 1 by 2 to the power k, which is less than equal to half plus half, which is 1. Okay. Norm of this is less than k equal to L to infinity, not L to infinity. This is what 1 to n, etc. Okay. Then we are getting this one. Okay. Since t is continuous, therefore image of Tzn will go to Tx, and thus Tx is equal to y. Hence prove the result. Okay. Thank you. This all.